Anyway, I'm going to be talking a little bit about exascale computing, not the first at this conference to have done so. And of course, since disclaimers were popular yesterday, I thought I would provide one of my own. I used to be a staff member at Argonne and did other things in other institutions, but now I'm a consultant. I'm not a staff member, and so I'm not representing Argonne in a formal way. And of course, being as old as I am, I have a lot of opinions and biases that have no foundation whatsoever, but I still express them. So that's what you're going to get. Now, I was involved, as Thomas Sterling mentioned yesterday, with Thomas on something called the Petascale Initiative. So what's different about Exascale Initiative from the Petascale Initiative? Well, for one thing, there was no Petascale Initiative. It was petaflops. Okay, well, a couple of things. One is, it was the administrator of NASA at the time in 1993, Dan Golden, who said, you know, we really should look at, you know, petaflops computing. People are just starting to look at teraflops, and he thought that was short-sighted. Now, what he had in mind, in fact, was intelligent design. So he was the guy who really got things going, in a sense, and Thomas and I foolishly decided, well, we can organize a workshop and get the right people involved and start looking at the issues. So in February of '93, we had this workshop on enabling technologies for petaflops computing. The other difference is that that workshop was sponsored by 6 agencies. You know, people just said, oh, seems like a good idea. And so NASA provided money, NSF, DOE, ARPA. This was one of the periods when it was ARPA instead of DARPA. You know, it goes back and forth. NSA, and then BMDO, and I had to look it up last night to see what did BMDO stand for, the Ballistic Missile Defense Organization. Another difference is that petaflops initiative was at a time when petaflops were a factor of 10,000 away from the peak at the time, not a mere 1,000. Now, for the exaflops, of course, there have been a number of efforts. I'm going to be speaking primarily about the DOE part. And one thing that I'd say was a little bit different is that DOE decided rather than the build it and they will come approach, it should gather a lot of information about, well, what would be good about having exaflops computing, or exascale, and let's look at applications. And so there were some preliminary meetings called town hall meetings, and then 8 workshops, each of several days duration, each of which produced a pretty weighty report. And they were on different topics: climate science, nuclear physics. I think you can probably read those. And then those were followed by technology-oriented and cross-cutting workshops. I'll say a little bit about that later. And around the same time, Jack Donguera and Pete Beckman initiated this international exascale software project, trying to make it a global effort. So we had these scientific grand challenge workshops, which were all applications oriented. And the reason for me putting up this slide is for those of you who can write fast or memorize quickly, at the bottom it gives you a very lengthy link to the site where, well, one of the sites where you can get all the reports. They're all available in PDF format, as well as the ones for the cross-cutting workshops. So, not a surprise to you, I think, that every one of those 8 fields of applications said, oh, there are a lot of things that are really exciting that we could do if we had exascale computing. They also identified, you know, some issues that they saw based on the current projections of what the machines would look like. Namely, there would be some challenges to be met. So I'm going to say a little bit about the challenges and opportunities and some of the work that's gotten underway. And I'm focusing on the DOE Office of Science and the NNSA, the Nuclear National Security Agency, and the Advanced, I forget what ASC stands for these days. It used to be ASCII activities. But that's not to indicate that they're the only ones that are doing things. Certainly DARPA, as you heard, has a great program currently in effect. NSF has provided funding for the ISP meetings. The G8s, there's 8 countries have a research council, and they did an initiative on multilateral research, interdisciplinary program on application software towards exascale computing for global scale issues. Strangely, in Europe, they like to have fairly long titles for their programs, but NSF is a source of those, and they're funding primarily applications. So fusion, for example, was one. European Union is doing other things, and so on. So given those workshops, and you heard plenty about the findings, this chart shows pretty much the party line of DOE. Why exascale? Because of the science, U.S. leadership, and broad impact. There's a hope that the Exascale initiative, although it's aimed at the very high end, will also help the missing middle eventually. And DOE will do various things on the right-hand side of the slide. I put in blue supporting the research efforts in applied math and computer science and creating close partnerships with computational computer scientists, applied mathematicians, and so on, because I'll be talking a little bit about some of those efforts that are underway. Now, so DOE in part wants to guide the evolution. So in my view, being an old guy, this is nothing new. Seymour Cray certainly took input from people who were doing both nuclear weapons and climate modeling in the late 60s, early 70s to help design his machines. And so co-design can influence the evolution of systems, but only up to a point. We're not in the days where people like Seymour could start from scratch, essentially, or build on previous not so good vector machines and come up with something that really worked well. Co-design nowadays also has to involve mathematical models, programming models, algorithms, because they need to be modified. In some cases, it's just adaptations of current ones, but in some other cases, we may have to use new ones, including the mathematical models. Now, one of the things that I did, which had a slight influence on DOE's plans, is after the 8 applications-oriented workshops, I suggested to the DOE Office of Science, well, now, if we really want to do something, we should look at what are the issues that tended to come up in many of those application areas, and also issues that come up with the various ideas of what the architectures will be like. So let's call them cross-cutting issues, and let's try to identify those, because those can help direct the co-design effort, as opposed to having each application community, basically push or lobby for getting their perception of their needs met by the co-design effort. So the idea is to have, through the co-design effort, identifying cross-cutting issues, a better match of the applications than would otherwise be the case. It's not going to be a perfect match, and a lot of things can't be changed given that industry is pretty much tied to CMOS and to the current memory technologies, but at least we can improve things. So now co-design, of course, as I say, it's been done, but it involves a lot of players, and it's a contact sport, so that makes it difficult right away. Communications, and the fact that you have to involve industry and system architects, computer scientists, applied mathematicians, the application developers, and application scientists, and there's supposed to be interaction among all 5 of those communities. So I don't mean to indicate that it's going to be easy, but if we don't do it, I think we know the answer will be not very optimal. So this slide is the current version of the DOE's plan for their Exascale program. So it's got 5 pieces to it: platform R&D, critical technologies development, software and environments, which IESP is one of the key, but not the only project, a co-design approach, and then platforms. And as you can see at the bottom, the hope is that today's capability platform becomes tomorrow's desktop, and that will continue even in the exascale regime. This is an eye chart. I only put it up because it's got in the two right-hand columns the so-called swim lanes. So the general thought is that, well, you have to have machines, real machines developed over the next decade, or else you won't ever get to exascale. And so there are two broad guesses as to what the machines would look like. So they call those swim lanes. And again, online you can see the full report of the Architectures and Technology Workshop report. But unfortunately, the timing is such that the swim lanes are treading water. That is, DOE has a plan or has stated that it will fund actual selection and acquisition of at least 2 paths to exascale in terms of architecture, using vendors and partnerships. But right now, and this is my guess, it may be a couple of years before that gets started. Now, if you do co-design, and you remember that picture with the 5 blobs on it, you're supposed to have the industry people involved all the time. So you can do that informally, but until we actually have partnerships with industry, that will make it more difficult, unfortunately. And on the platform research and development and critical technologies, those left 2 panels of the 5 that constitute the nominal program, there's some R&D being funded. Fortunately, the DARPA UHPC is addressing a lot of those issues, and we hope it continues. So as I mentioned, we did have a workshop on cross-cutting technologies, and the findings are in the report. You don't have to read this slide. But one of the things that I tried to do in that workshop was to get the mathematics, the applied math, the mathematical models, and the computer science issues more involved in the planning, because those, in my view, had been somewhat ignored in the previous workshops. And so, as you might imagine, things were identified, such as uncertainty quantification would be critical, multi-scale, multi-physics modeling, statistics of rare events, and memory management. More dynamic control system resources. There were a lot of allusions to that yesterday, both in the runtime systems and in the programming models. And DOE listened to the output of those workshops, and in fact has already funded some exascale research and development. There was a kickoff meeting earlier this month that brought together 34 project PIs and co-PIs that were funded. And in the blue, at the top here, you can see yet another somewhat long link that gives you information about those 34 grants in case you're interested in the details. As you can see on this slide, they did fund some projects in uncertainty quantification, advanced architectures, software stack, data management, and co-design. And there were lots of proposals, and only a few, of course, funded. For example, for UQ, 90 proposals, 6 were funded. Advanced architectures, 28, 6 were funded, and so on. Now in blue, I have that there is a planning grant for the Exascale Software Center, which I'll describe momentarily, and then at the bottom that there are planning grants for 7 co-design centers that put in proposals, but they don't actually have the center funding. On the other hand, they do have planning grants. So this is an attempt to get things started, even though, as I said, the platforms part, the swim lanes, is temporarily on hold. There's just not a budget for it yet. So software, since that's such a central issue, and even though we don't know what the target architectures are in detail, or will be, I think it's sensible to go ahead and start looking at the system software especially. So the Exascale Software Center that's doing the planning, and the plan isn't done, so I can't give you a lot of details. The idea was to aim even now to deploy software, an Exascale software stack on the platforms. So when I use the word deploy, I'm implying that it's going to be maybe 10 years from now production software. So getting started now to work on the issues that need to be dealt with at the Exascale, and of course having to work in the context of what the platforms will be, the cross-cutting technologies that are needed, and the co-design application teams. Now, where do you draw the line? Certainly the vendors will be supplying software, and some of the application capabilities will certainly be done by the application teams and not by an Exascale Software Center, but somewhere in the middle, some of the basic tools and some of the operating system, the runtime systems, and so on need to be done by somebody, and the Exascale Software Center is hoping to do some of that. Yesterday you heard some interesting approaches, for example, from Thomas Sterling on runtime systems oriented and programming models oriented ideas. So those you could think of as potential examples of things that would be done. And the scope is in 5 broad areas at this point. Again, this is preliminary planning. So you have to deal with programming models, advanced language features. Currently, just about everybody uses MPI at the large scale. So rather than abandon it, maybe improve it and perhaps mate it to some thread-oriented programming. Try to provide interoperability for the different programming models and deal with fault tolerance. Lots of tools. A very obvious one would be you want to be able to measure what's going on in the system and analyze the results. You want to be able to simulate the systems before they're fully built so that you can try out ideas for programming them. Math libraries, not everything, but it's pretty certain that some people will still need dense matrix libraries. And now sparse iterative methods may be more important in the future. Operating and runtime systems, I didn't include any detail under that. That's a huge area. And data, one of the things that essentially all the application workshops identified is, we don't need just more flops or memory. We need ways of handling data. The massive output from the simulations as well as input from sensors. And right now we're not in very good shape for that, even with the petaflop systems. So there are plans for a lot of activities to deal with the data analysis, storage, finding things, checkpointing. Should be in quotes, I suppose, because maybe it wouldn't be the kind of checkpointing we do now in dealing with faults. So the Exascale Software Center is, I think in a couple of weeks, going to be sending this plan to DOE, and we'll see whether it gets funded or not, but they have a planning grant for it. Now, one of the things that you can imagine is that there's a lot of, I'll call it arm wrestling or debate as to, well, does it make sense to do evolutionary things? Do we stick with Linux and make it suitable for Exascale? I mentioned MPI. Do we stick with, this dog-eared old MPI programming model as opposed to something completely new? Well, remember that the goal of the Exascale Software Center was to do production software, and I think it's unlikely that you can go completely revolutionary. Where are the compilers going to come from for the advanced new languages that have not even yet been invented? And so I think both evolutionary and revolutionary R&D, and not only research and development, but also deployment, has to be carried out. And that's my opinion. And on the other hand, even as one pursues perhaps mostly evolutionary R&D in the context of the center, there are the research projects. I mentioned there were 34 of them, which aim at a lot of related areas, and you certainly keep track of them, and when something looks like it's going to pay off, maybe through simulations or early experimentation, then you see, can we import it, work with that group, and productize it. But to just do revolutionary, I'd be scared as hell to only take that approach. And when would you integrate the research ideas? Well, you evaluate the risk periodically. Remember, co-design is a continual process. You don't just do it once, one spin around that wheel, and then you know what you're doing. Things are going to change. Even the applications are going to change. So it isn't just a matter of doing the same applications faster or with more accuracy. There will be different physics added and different models. So speaking of applications, 7 of the co-design center proposals didn't get their center funding, but they do have planning grants. And so the first one, I say sadly, is exascale simulation of advanced reactors. That's as in nuclear reactors for generating electricity. I continue to think that nuclear energy production will be important worldwide, but certainly the recent events in Japan are going to make it very difficult to get acceptance of that. Nevertheless, research needs to be done, and there are a lot of things that can be helped in terms of safety as well as productivity of the reactors with advanced computing. Don Lamb is here. He leads the Energy Density Physics Co-Design Center. There's one on fusion, one on materials, on chemistry, combustion, and Earth system simulation, which would include climate modeling. So these are being put in place, and these are very large teams of very qualified people who are very excited about the prospect of having a hand in the co-design process, so that hopefully 10 years from now the machines that emerge and the software will be better suited than would otherwise be the case for their applications. Again, these are my thoughts. I'm not talking very much about the technical challenges because they were dealt with so thoroughly yesterday, but I see some real challenges in executing the program, and by program I mean the actual projects that will result in a real exascale system or various exascale systems. To me, how you implement and manage such a program may be the biggest challenge. Why? Well, in my view, it would be great if you could think of a worldwide effort as one project, something like LHC for high energy physics or ITER for fusion, and that you have people combine their funding, but there's one project and people work together. That would help. There's a lot of work to be done, lots of good brains scattered all around the world, and lots of technologies. And we know that it can be done. The International Exascale Software Project that Jack and Dongar and Pete Beckman have been leading, many of you have participated in a fairly short amount of time produced a software roadmap that's online, and it integrated input from lots of world regions. Meetings were held in Japan, Europe, as well as in the United States. And so, people at the working level are certainly willing to consider that. But of course, scientists as well as institutions, national labs, and governments also have a competitive spirit. So that tends to mean that you have, well, sometimes healthy competition, but in my view, sometimes needless duplication. So I'm particularly not very pleased by the fact there's now an EESI, the European Exascale Software Initiative, given that the people who started that were very actively involved in the international Exascale software project. I guess that's human nature. You know, as I mentioned, I would give you my biases and opinions, and I wish it weren't so, but you know, we're a competitive breed, we humans. But it doesn't stop there. Different government agencies, even within the U.S., have different congressional committees that approve their budgets on different time scales. Even within the Department of Energy, the NNSA part of DOE is their budget is controlled by different committees in Congress from the Office of Science. So you have different funding sources, different schedules for getting the funding, different ways of selecting and managing the research, development, and deployment projects. And so to have a unified program, which is what I wish could be done, would be very difficult, probably impossible, in fact. So I think it's a real challenge to have an Exascale initiative or program given all these procedural issues. Now, within DOE, I think there's a very strong commitment from the NNSA side and the Office of Science side to, in fact, have a coordinated plan. I don't think the funding is going to be mixed, but at least looking at what needs to be done, what are the gaps, and having a plan to address those gaps and developments. That, I think, over the next few months, we'll end up with a coordinated plan. There's a good start on that already. So I'm not completely distraught, but I wish we could do more, especially internationally. Another big challenge of having this plan is, well, we talk about co-design and working with vendors. And now if you have people getting very sensitive NDA information from various vendors, how comfortable are the vendors going to be with that? If you start implementing things and trying them out even on simulators and report on your results openly, that's going to perhaps give away some sensitive information that the vendors don't particularly want to give away. So the intellectual property and NDA issues across the vendors will be difficult. My own experience in working with vendors in the long distant past is that almost always the timing was wrong. You know, I'd get a new system, they say, please evaluate it, put some software on it, and not me, but my group would do, I thought, a pretty good job, give excellent feedback, and as we delivered the feedback, we were told, sorry, too late to implement any of these wonderful ideas, because you know, we're already turning the crank, and the next generation can't be changed anymore. Another issue is, you know, how do you select the applications that really have the most impact on guiding the system design? Is it going to be the people who have the most eloquent spokesperson, or you know, somehow one decides, well, you know, fusion is more important than climate modeling? And just to choose some silly examples. And of course, can we really change that much in the vendors' plans? You know, they've got a huge customer base, and we heard about Intel wanting to do more with the missing middle. And you know, how much can we really influence the products, given that we're just a small part of the user community? And even we don't want radical changes anymore than we have to accept. We already have plenty that are coming up. So my view is that certainly there are a lot of technical challenges as well as opportunities, but actually getting something done is not so easy. And so I call those perhaps management plan challenges or program challenges. So in summary, although I've perhaps been a bit pessimistic in what I've said, on the whole, I'm delighted that in some sense the Exascale program is underway. Now it's underway with a staggered staff. The ordering is suboptimal. You know, we're starting a lot of the R&D and Exascale software development before we've really looked at what the hardware is going to be like, and not a lot of R&D has been done on new functionality in the hardware or on programming models, and the funding is very modest so far. But still, I'm glad that things are getting started. You know, if you don't get started, you won't get anything done. So I'd say, fine, let's do something, even if it's wrong, because at least we'll find out that it's wrong and improve it through this co-design effort and iteration. So those are my remarks, and I welcome your comments and brickbats. Thank you.